You clicked because you want to understand why gold refuses to rust in your electronics. The real stakes involve the reliability of every device that depends on stable electrical connections over decades. By the end of this video, you will see how relativistic quantum mechanics forces a specific atomic behavior that makes copper fail while gold succeeds in critical hardware interfaces. We often treat gold plating as a marketing flourish or an unnecessary luxury cost added to consumer electronics. This assumption is dangerous because it ignores the fundamental physics governing electron transport at the interface level. In high-reliability systems, the choice of material is not about aesthetics or brand prestige. It is a hard constraint dictated by how electrons behave inside atoms under extreme conditions. To understand why gold remains irreplaceable in aerospace and medical implants, we must look past chemistry and into quantum mechanics. The standard explanation for corrosion focuses on electron loss. When copper oxidizes, it loses outer shell electrons to oxygen molecules, forming an insulating layer that blocks current flow. This process seems like a simple chemical reaction driven by environmental humidity or heat cycles. However, the reason gold does not undergo this same fate is far more exotic than typical chemistry textbooks suggest. The inertness of gold is not just about having full electron shells. It is about relativistic effects altering those shells in ways that defy classical intuition for lighter elements like silver or copper. In heavy atoms with high atomic numbers, inner electrons travel at speeds approaching a significant fraction of the speed of light. This velocity increase causes their mass to effectively rise due to special relativity. As these core electrons become heavier and more massive, they pull closer to the nucleus, creating a stronger electrostatic field that affects all outer shells. For gold, this relativistic contraction squeezes its 6s orbital tighter around the nucleus than it would be in non-relativistic models. This compression raises the ionization energy significantly, making it energetically prohibitive for an oxygen atom to rip away those electrons and form a stable oxide bond. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Simultaneously, these same relativistic effects cause the d orbitals of gold to expand outward into the valence shell region. The result is a filled 5D subshell that sits just beneath the contracted s shell, creating a unique electronic landscape where oxidation products cannot easily nucleate or stabilize. This atomic rigidity creates a fundamental barrier against rusting that copper simply cannot replicate. Copper's 4s orbital does not experience these relativistic contractions to the same degree because it lacks sufficient nuclear charge and electron velocity. Consequently, copper readily loses electrons in humid environments, forming cupric oxide, which is an electrical insulator with high resistance. This quantum mechanical stability dictates a hard engineering constraint that defines modern hardware architecture. In high-density connectors and bonding wires used for microchips, the requirement is to maintain sub-10 ohm contact resistance over decades of thermal cycling without degradation. Gold-plated contacts achieve this because their surface remains chemically pure and conductive, regardless of atmospheric exposure or temperature fluctuations. Copper alternatives require complex hermetic sealing solutions just to slow down oxidation enough to be viable for short-term use. But these seals add cost points that become failure mechanisms in themselves over long operational lifespans. Consider the specific trade-offs faced by systems architects designing for aerospace applications. The production cost of gold is orders of magnitude higher than copper per unit weight. Yet practitioners view this expense not as a luxury purchase, but as an insurance policy against catastrophic signal degradation. Benchmarks show that while copper connectors can fail intermittently within years due to oxide buildup, gold interfaces maintain their electrical integrity through thousands of thermal cycles without requiring maintenance or replacement. This zero-maintenance requirement is critical in environments where physical access for repair is impossible or prohibitively dangerous, such as deep space probes or implanted medical devices. The failure mode that drives this decision is galvanic corrosion combined with oxide-induced signal degradation. When dissimilar metals interact in the presence of moisture and an electrical current, electrochemical reactions accelerate material loss at specific points. In a copper system, even trace amounts of oxidation create microscopic gaps or contact resistance spikes unpredictably. These intermittent failures can corrupt data streams or trigger false safety shutdowns in critical systems. Gold eliminates this risk entirely because its relativistic stability prevents the formation of any insulating oxide layer that could bridge those connections and break the circuit path. However, it is crucial to qualify what gold's inertness actually protects against. While bulk oxidation is effectively impossible for gold under normal operating conditions, other failure modes remain relevant engineering challenges. Gold whiskers can grow out from plating surfaces over time due to mechanical stress or lattice strain, potentially causing short circuits between adjacent contacts. Additionally, in specific industrial atmospheres containing sulfur compounds, gold can suffer from sulfide tarnishing, which alters surface conductivity even if it does not form a thick oxide layer like copper rust. This means gold is the solution for chemical stability and oxidation resistance, but it is not a panacea that solves all interface failure modes, including mechanical wear or stress-induced structural migration. The engineering reality is that no other transition metal offers this specific combination of high conductivity and absolute surface inertness derived from relativistic quantum effects. Silver oxidizes just as readily as copper, despite being more conductive in its pure state, making it unsuitable for exposed long-term interfaces without heavy plating protection. Platinum resists corrosion well but lacks the same level of bulk electrical conductivity required for low-loss signal transmission at high frequencies used in modern RF systems and 5G infrastructure. Gold occupies a unique niche where relativistic physics creates an atomic structure that is both conductive enough to carry signals efficiently and chemically rigid enough to refuse reacting with its environment. This specific property transforms gold from a precious metal into a critical materials constraint for any system demanding decades of reliability without active maintenance protocols. The cost differential becomes secondary when weighed against the risk of total system failure caused by inevitable copper oxidation mechanisms that no amount of sealing can fully eliminate over extreme timeframes. Engineers do not choose gold because it is expensive. They are forced to select it because relativistic quantum mechanics leaves them with no other viable option for maintaining sub-10 ohm contact resistance in harsh environments where signal integrity cannot be compromised by the formation of insulating surface layers. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.